So she said B2H6 and hydroxide and H2O will do exactly that step. So she now knows that step. Okay, so that's good. We've gotten somewhere. We have kind of a problem with this, though. We have to do the complete synthesis, the big purple arrow across the top. Why do we have a problem? Which I should have seen earlier when we were talking about it, but I didn't. How do you do this reaction, that first step? Okay, so according to our synthesis, what we now need to go through and do is decide what type of reaction happened there. Is it acid-base? No. Is it an addition? An elimination? Substitution? Radical? Uh-oh. That step is not possible. Meaning it's not a one-step system. We have to go somewhere else and then go up to that. Okay? So in playing around with the pieces, they did find a good piece. Okay? That middle one. Because they know now how to make that last transition. That's useful. But they're now missing another step. Okay? So let's work together. What piece could go in there? What needs to happen? We need to identify the chemistry. What is the chemistry on the starting material? Pi bond. What is the chemistry in the product? What is it? It's this structure here we're aiming for. Because we're okay with the next part. What is the chemistry in both those structures? A pi bond. Okay? So I need to address that pi bond reactivity. Okay? How could I go through and do that? Would it be acid-base? Acid-base reactions don't involve pi bonds, so it's probably not acid-base. Substitution. Substitution doesn't involve pi bonds, probably not substitution. Elimination. Making a pi bond, that's possible. Okay? That could be over here. We could be doing an elimination. Okay? But if I did an elimination, what does that mean is not here? No pi. If there's no pi there, what does that mean that first step needs to be? An addition. Okay. So what are some possibilities? To do an elimination, what needs to happen? First step of almost all leaving group, or sorry, what did you say?
2 sigma bonds need to be broken.
2 sigma bonds need to be broken. One of those sigma bonds needs to be, begins with an L, a leaving group. Okay. What would be a good leaving group? Bromine. Okay. Why would we pick bromine as a good leaving group? It's stable by itself. There's another good explanation for why we pick bromine as a leaving group. What's that? Electronegativity, yes. Another reason. Size, that's stability with it. Yes. This is a reaction that came off of a synthesis activity, and in that synthesis activity we had a bunch of little tiles given to you for you to look at. And when we look at those tiles, we have 2 choices of leaving groups, bromine or OH. Which of those are decent leaving groups, or the best leaving group? Bromine, because of its size, because of its electronegativity. So why are we picking bromine? Because that's what we have to choose from. Okay? So we need to somehow put that bromine on there. Okay? Where is that bromine going to go? Okay? Well, it has to be located in the place where it overlaps the addition and the elimination. Where's the overlap between those two? The tertiary position. That has to be where my bromine goes. If I picked the terminal carbon on that methyl group, that's now outside of the ring. I can't do an elimination to get the pi bond inside. If I picked the secondary carbon, if you will, of the pi bond inside the ring, well, there's no chemistry there in the starting material. It couldn't do the elimination. So what I'm looking at is where that functionalities overlap to allow me to put in that leaving group. Okay? I now have a structural piece. Is that structural piece one of those little tiles? Oh, look at that. Cool. Okay. So now the question is, we would go back home and say, well, I need to do an addition. Where what am I adding in that first step? I'm adding bromine. Is that it? And hydrogen. So I now have an option. I can go into the textbook. If I have an old or a different textbook, I can look up the alkenes, find addition, find HBr. How do I add it? How would it work? Does that work? Okay. If we have our textbook, the Cardy textbook, we would look up the addition reactions and look through the addition reactions chapter until we found an alkene and said, does the alkene react with hydrogen and bromine? What is the result? Does that work? Yep, there's our reagent. Okay. Same concept for the elimination side. When I did the elimination, what else happened? What happened in the elimination reaction? Loss of the bromine, loss of the hydrogen. I now have information that I can now go up or go to the textbook and look that information up. Okay. Eventually, by the end of the semester, where are you going to be looking up that information? In your brain. Okay. You're not there yet. Don't stress about it. If you already are there, awesome, great, good for you. Don't tell anybody else because they'll punch you. Okay. Use the textbook, look that up. The point of the activity right now is to kind of find those pieces and see where we're going. Okay? You then go look those up, okay, outside of class. You should have enough time in your group to come up with possibly 3 or 4 structure steps. Okay? You can each go home and look up a different one. When you come back, you can then share your results. This is what I think works. The rest of the group can look at it and be like, no, that's wrong. You can't read. Right? HCl is the wrong reagent to use because we're adding bromine. You're wrong. Okay? Or, oh yeah, that kind of looks like it's reasonable. Right? Or wait, isn't that supposed to be anti-Markovnikov versus Markovnikov? How would we adjust for that? Okay? Theoretically, your research outside of class will solve all those issues so that when someone asks, but wait, you're putting the bromine in the wrong position. Doesn't that add the bromine in the other place? You'd be like, no. Because we're doing it with a radical, it puts the bromine in the wrong position. Here, where are we putting the bromine? All right, position.
Right position.
Right. So that's what I want you to do with the activity. It's not just about getting the answer. The process is much more important at this stage than the answer. Make sense? Okay. Feeling a little bit better about the synthesis activity? You guys ready to rock it on Monday?
Yeah.
Next Wednesday? Okay. Addition reaction. So we talked about pi bonds, or in particular non-polar pi bonds, acting as bases. Okay, so we throw in an acid, okay, picks up the hydrogen, neutralizes that acidic hydrogen, and then a nucleophile can come in and stabilize. Right? What happens if it's not reacting with an acid? Okay? We have other sources of positive charge other than hydrogen. That's our electrophiles. Okay? So what are potential electrophiles? Okay? That's where a lot of Chapter 12 and 24 is looking at. Officially, Chapter 12 is all review. Okay? And in fact, the sections in 24 are also review. Right? We went through them fast in first semester, or maybe not at all in other cases. Okay? So we just have to build and go back and constantly review those. Okay? In all cases, we're getting the same basic system. Your electrophilic atom, the one that is most positive, will go to the most negative atom of our pi bond. Okay? The one that is most negative of our reagent will go to the most positive of our pi bond. Almost all of them involve some sort of cyclic intermediate, okay, which is another big differentiator from the pi bonds acting as bases. Okay. Why did we not get cyclic intermediates And we had the pi bond act as a base. What's the first step? What do we make? Why is this not cyclic? Hydrogen does not have electrons. Why else is it not cyclic? Hydrogen is tiny. It is such a tiny atom that it can't physically bridge the gap between the carbons. So it can't actually, even if it had some extra electrons, which it doesn't, but even if it had some extra electrons, it is so small it can't bridge the gap between those two carbons. We can't form a cyclic intermediate. If we instead moved this to, say, Br2, okay, and this is where our electrophiles become weird, because when we think about bromine, what do we think about bromine as? A nucleophile, or a leaving group. It's got a bunch of electrons. And yet, as soon as I make it next to another bromine, what happens to the bromine? It acts as an electrophile. It ends up taking electrons, which seems really, really bizarre. Okay? That's because the other bromine steals the electrons from it, and one of them becomes partially positive, the other one becomes partially negative. So our electrons can come out and share. If we were to draw the exact same result as that we had with our HBr, or sorry, our hydrogen, or our acid. Okay, we said hydrogen couldn't form a cyclic intermediate because it didn't have electrons and was tiny. What can you tell me is different about bromine? It has electrons, and it's huge. Guess what? That bromine can shift its location ever so slightly, to show an E, to bridge that gap. The result is we end up with a cyclic intermediate. And if we look at that, you might say, well, isn't that kind of ugly, Mike? Well, what's kind of ugly about it? I don't understand. What's that? Yes, technically we need wedges and dashes. We can add those in a second.
But doesn't the bromine have a positive charge?
Bromine only wants one bond. How many bonds does it have?
Two.
Okay? It only has two lone pairs now. That bromine is positively charged. Okay? Does bromine want to be positive? No. So this structure is now dying to break open. But to break open, what does it need? Something to react with. What's that something? Need to be. We need electrons. In the case of Br2, what happens to also be floating around? Bromide, which can now come in and stabilize our structure. Okay? Back to our wedges and dashes. Why do we need wedges and dashes on this structure? Both of those carbons, one of those carbons is a stereocenter. Okay? Why is the middle one a stereocenter but the end one not? The end one has two hydrogens. The instant I have that stereocenter, I have to specify our wedges and dashes. Okay? So if I went through and showed that as a wedge, I don't technically need it on the other one, but it's now a cyclic structure. It being cyclic is now also going to force that other carbon-bromine bond to be what? Why does it have to be wedged? Okay, well, if this is my carbon-to-carbon on my iPad, right? And this is now a bromine. Okay, that bond, right, that's wedged, right? It's coming up. How do I have a down bond to the bromine from the other carbon? I physically cannot do that. Okay? It is impossible with a three-membered ring. Okay? So it has to be wedged. That brings in that stereochemistry that we would then have to evaluate when we go through and look to our final products. Okay? That bromide could then come in and stabilize the structure. That bromide as a negative is going to need to find something positive. What's the positive it reacts with? Why would you say bromine? I heard somebody say it. It's positive. Oh, why not? Negative to positive. Please don't write that. Okay. What is the issue with that? The bromine has too many electrons. Okay. It already has its octet. If we try to share more electrons, it exceeds its octet. It can't do that. Okay. That bromine being positive is dying for electrons. That is true. Is it easier to find electrons outside the structure or inside the structure? If you want to go buy a sandwich, do you go ask your parents for money or do you check your wallet first? Okay. Unless you know your wallet didn't have any money in it. But then you still checked it. You would still check your wallet first. Okay. Why? Your wallet with money is closer to you than your parents. Okay. You don't want to then drive over there. Okay, can I have some money? No, why do you need money? I want to buy a sandwich. What are you going to put on that sandwich? It's none of your business. I'm a grown person. Leave me alone. You're a grown person. Go make your own money. Right? You don't get any of that. Right? So it's a harsh world. So where is that positive bromine going to find electrons? It's going to go within the structure. Where's the closest source of electrons?
In the bond with the carbon?
In the bond with the carbon. Interesting way he said that. In the bond with the carbon. How many bonds are two carbon and bromine? There's two of them. So it's not the bond with the carbon. There's two carbons that I could be looking at. Which one do I look at? Why the stereo center?
Secondary carbocation? Or more?
Do you see a carbocation? No. Is there a carbocation in this mechanism? No. Okay, so I understand where you're going with that, but no. Can't use that. Okay, it's the more substituted position. Is my nucleophile expected to do a backside attack on a more substituted position? No. So again, decent answer, not working. There's a really big piece that we're missing. For it to do that attack, what else must happen? Which bond? The carbon-bromine bond has to break. That bromine has to be willing to take the electrons away from the structure. Okay? If it is really willing to take the electrons away, I'm going to have my nucleophile attack the more sterically hindered site because that leaving group is already saying, F this, I'm taking the electrons. Okay? If it is not a good leaving group, then it can't take the electrons, in which case our nucleophile will have to attack the other position, the least sterically hindered. Is Br positive a really good leaving group? Yes. Why? When it leaves, what is its charge? Neutral. That is a phenomenal leaving group, which is why the bromide is our nucleophile. That Br minus will come in and attack the more sterically hindered position. That's why the attack happens there. So when we're looking at breaking open these cyclic structures, we have to evaluate the ability of the leaving group. If it's a good leaving group, attack the more substituted position. If it's a bad leaving group, attack the less substituted position. Okay. Super relevant if we say jump to MCPBA. Okay. When we look at the result of that reaction in its chemistry. Okay. So, electrophiles. If we take a look at our list here, I've broken them down according to the cyclic intermediate ring structure they're making. Okay? Those intermediates may be mechanistic intermediates. They may be final product intermediates, depending on stability of those pieces. Okay? Notice I've got some of them highlighted. Okay? In BR2, there's only one thing, but the bromine's highlighted. Why is the bromine highlighted? Top of the slide, this is addition reactions with electrophiles. Why is the bromine highlighted?
It's the electrophile.
It's the electrophile. MCPBA, what did I highlight? The P, because the P is the electrophile. What's the P in MCPBA? It's not phosphorus, unfortunately. It's a peroxy. Right? CH2N2, what's the electrophile? The carbon of that structure. Mercury X, where that X is not referencing halides, it's referencing pretty much anything. If you see mercury with something, it's fitting in this tri-intermediate. The mercury is acting as the electrophile. Your tetra-intermediates, we really only have one, HBX. Oh, that was interesting. We saw that one already, thanks to Lydia. That was in our synthesis. B2H6. Guess what? B2H6 is HBX2. The same reagent. It just happens to dimerize. The penta-intermediates. OSO, KMNO, and O3. That's a bit bizarre because I'm highlighting more than one atom. Why am I highlighting more than one atom? More than one atom reacts. To have a penta-intermediate, that's pent 5. 2 of them are alkene. I need 3 other atoms. All right, those 3 other atoms are coming from the pentastructures. Right? So, let's poke at these a little bit. Okay. Strict electrophilic additions become a lot more kind of complicated. So when we go through and look at these, your 3-member transition states. When we look at our general form, our alkene plus our Lewis acid and a leaving group, and then a nucleophile. Those are your basic components. Sometimes the nucleophile can be attached to the Lewis acid, sometimes it's a separate piece. Okay, so we've got all of those kind of components together. If your Lewis acid is a nucleophile, then we get a 3-member transition state. Okay, let's process that. Lewis acid is a nucleophile. What is a Lewis acid? An electron pair acceptor, which means what charge would we expect it to have? A positive. A nucleophile is what? An electron pair donor. The charge we would expect it to have? Negative. What the F? How do I have a Lewis acid also be a nucleophile? That bromine has now accepted electrons. If we look at our mechanism, what did the bromine do? It accepted electrons and donated electrons. You have a single species acting as both a Lewis acid and as a nucleophile. Okay? That is going to be a tip-off that we're looking at a 3-member transition state. Okay. How about the mercury? The standard one is with 2 acetates. What happens with mercury? Pi bond attacks. One of our acetates leaves. Mercury, being a nasty, awful metal, also happens to have d electrons, which what is the mercury doing? Accepting electrons, Lewis acid, donating electrons, nucleophile. The equivalent of our MCPBA. Whoops. Double whoops. Oh my God, tons of arrows. Yes, breathe. MCP, remember the P was our electrophile, the P was for the peroxy. The peroxy is that oxygen-oxygen single bond. Okay, so we look at that tail oxygen, that is part of our peroxy. That's what allows MCPBA to react. What is that oxygen doing? It is accepting electrons from the pi bond, okay, thereby allowing it to break the oxygen-oxygen single bond. Okay? It's a high-energy bond. Why is that a high-energy bond? which atom, oxygen or oxygen, is going to steal the electrons from that bond? Ah, good answer. The oxygen. Okay? They're both highly electronegative. They're both pulling on those electrons. That bond is insanely stressed. All we got to do is poke it and it explodes. Okay? One of the reasons why hydrogen peroxide is dangerous. Okay? That causes a cascade of events that shuttles electrons all the way around, and I can then take electrons away from that hydrogen-oxygen bond to donate in to make my three-membered ring. Okay? The oxygen is acting as both a Lewis acid and a nucleophile.
What would the final bond look like?
So what happens? We go through our general mechanism. Our Lewis acid with our leaving group set up. Okay? In its simplest form, that's what we would get. Okay? We end up with our three-membered intermediate. Depending on what our Lewis acid is, it might be charged. Okay? If it is charged, that's when the nucleophile can come in and start to collapse your structure out. What if it's not charged? What if I look at this and that's not charged? What does that mean?
It might be stable.
That means that intermediate is likely stable. So what happens? Rhymes with something. Nothing happens. The reaction stops right there, and that ends up being our product. That is the case with MCPBA. Because when we look at MCPBA, the reagent itself does not supply a nucleophile. Okay? In the case of Br2, what happens? Well, we'd have that positively charged bromine. Bromine doesn't want to be positively charged. We search the solution for a negative. If we add Br2, we've got bromide floating around. That can come in and attack. That was the leaving group. Does my nucleophile have to be the leaving group? Nope. In the case of Br2, I could just add straight Br2, or I could add Br2 and water. Water now has oxygen that can act as a nucleophile instead of the bromine. And we'd end up doing a hydrohalogenation because we added water and the halogen. Okay? So what we're doing within these slides is trying to find the commonalities and the patterns within them so that when we move to the reagents, we can say, okay, I can see how those work, how these fit. This is not just, here's a reagent, memorize the crap out of it, okay? Because I can't help you with that. All I can help you do is find patterns that can potentially make it easier. What happens if your leaving group is tiny? Okay. How about in the case of the one we were adjusting earlier? Okay, our BH3. Okay. Where's our positive atom in BH3? Oh, that's right. I don't remember that, Mike. Well, let's go back. Maybe Mike had a nice little convenient summary slide there. Oh, yeah. It says we're looking at H and B. Okay, so one of those is my answer. Go figure, considering what I just drew up was BH3, but it's neither here nor there. Maybe. Boron, H, H. Which is more positive, boron or hydrogen? If we look up the electronegativities, it turns out hydrogen has a higher electronegativity than boron, which means boron is more positive. We take this a step further. What is the hybridization of that boron? sp2, which means what is left over? A p orbital, and what can we dump into an empty p orbital? Electrons. The boron acts as our electrophile. The electrons come out. Boron's now like, oh my god, I got too many electrons, so it has to get rid of something. What's its leaving group? No, I don't accept hydrogen. Hydride. That hydride is coming out with electrons. Is that really tiny? Yeah. Guess what happens? It doesn't just leave. It immediately comes out and reacts, effectively forming a four-membered transition state. Right? And we now have that transition where we have all of those bonds now being connected. Okay? So it's looking at the patterns of what things are there and evaluating how that works. As we go through and look at our reagents and try and come up with where they match, what we need to be thinking about is, number one, which pathway are we running? 3-membered or 4-membered? Okay? The overall reaction is an addition reaction. So we're going to lose that pi bond. We have to add 2 new sigma bonds. Okay? The next part, structure and mechanism. The structure and the mechanism are what's going to dictate your stereochemistry and your regiochemistry. The regiochemistry is Markovnikov, anti-Markovnikov. Where did your positive and negative atoms go? Okay. Markovnikov is where did the hydrogen go? Okay. The reality of it is where are your positive and your negative atoms? Okay. What does it appear to be doing? The stereochemistry, wedges and dashes. Okay. 4-membered ring, Lewis acid in the leaving group. If we're doing this as a 4-membered ring, if I put the Lewis acid wedged, what does the leaving group need to be? Ooh, I heard 2 answers. Okay. Is this happening all at once or stepwise? At once. The leaving group is not stable. Okay? It is tiny, which means it must immediately react. Okay? Does that mean it can come all the way back around to attack from the backside? No, which means the leaving group must be wedged. What happens in the case of the top one? Okay. We look at our Lewis acid. If that is now wedged, where's the nucleophile have to come in? Backside, for a couple reasons. Why? Number one, the leaving group or a nucleophile is relatively stable on its own. It can float around. Okay? It can go anywhere that's favorable. Why can it not attack from the wedge side? What electrons? There's that 3-membered ring with the Lewis acid. Okay? So if we step back here, if we said that one was wedged, what's the other one got to be?
Wedged.
Also wedged. That was the whole, take a piece of paper, take one point, put your hand over the top of it, make one wedged. Can you make the other bonds dashed? Okay? It's not physically possible. Which means when the nucleophile comes in, it has to come in from the backside. Okay? So it's recognizing those patterns and seeing where those things slide around on you. Okay? So, our tri-intermediates. Okay? We take a look at the relationship between our products. And it helps if I'd actually numbered all these things. What is the relationship between our products? I've got those numbered 1 and 2. Begins with an E. They're enantiomers. Okay? When we run an addition reaction, we're reacting the pi bond. That's what we're showing at the very middle, right at the top. That's where we're starting. Reacting the pi bond. Those pi electrons can come out and react with our electrophile on one side or the other. Okay? Which means there are 2 possible results on where the electrophile can be located. Once the nucleophile comes in, there's now 2 possible results where the nucleophile can come in. This gives me the potential to make enantiomers. Why do I say potential? What happens if I get rid of the 1 and the 2? What is the relationship between those structures now? Begins with an I or S. They're identical because no stereocenter. I haven't labeled what those are, so by definition they're identical, which then means that's not a stereocenter. Same deal down here. So we have to be considering these things when we go through and run our reactions and keep them in mind. Okay? The electrophile in your tri-intermediates will act as a nucleophile simultaneously. Okay? It can't act as a secondary step. It happens at the exact same time. Okay? So no carbocations. Okay? So if we take a look, Br2 works. Okay? This is a fun little reagent. Draw the Lewis structure for that. It was like, Lewis structures? That's easy. Well, that's the easiest question I've asked so far today. Draw the Lewis structure. Or your best Lewis structure. And I think that's the issue. Trying to push your electrons around to make sure you get it. What do we see within this? Okay, we have a positive charge and a negative charge. Which, if I'm going to have charge, it better be positive and negative because the overall structure is neutral. Okay? What do you see as reactive?
The alkyne
What's that?
or the triple bond.
Okay, there's a triple bond there, so you see the triple bond is potentially being reactive. But argue it's not the triple bond.
Or the carbon.
Okay, the carbon has 2 electrons on it. That looks pretty reactive. So what if we neutralize that by reacting it with a pi bond? That should already make you go, ah, don't do that. What's wrong with that? Okay, that's negative to negative, right? What about like this? Really? This molecule has an interesting little feature going for it. If we cleave the bond between the carbon and the nitrogen, what do we have? What is this species? It's easier than that. It's easier than nitrile or anything like that. It's not nitrile. Nitrogen gas. What do we know about nitrogen gas? Insanely stable. Okay? So this molecule is saying, get out of here, nitrogen, because you're stable. Then we look at the remaining piece. What do we have there? What's its charge? Anybody have any problems with that being a 0 formal charge? Why does it look weird with a 0 formal charge? It has a lone pair, and anytime carbon has a lone pair, of course it would be negatively charged. Right? But no. Right? It only has 2 bonds. Right? It's missing electrons, so it should be positively charged. Right? Guess what this structure acts as? A nucleophile and an electrophile. It's a carbene. Okay? This reagent, diazomethane, insanely reactive. So reactive, you've seen your glassware with the little powder joints, the little, not crustiness, but you look at the joints and they're kind of frosted, right? You can't use that kind of glassware with this chemical. That joint is enough of a break, there's enough surface tension there that it will cause this compound to ignite and explode. People that routinely work with diazomethane are losing or have lost fingers. Yeah, it's one of those fun kind of compounds. Right? What's that? Because I want you to lose fingers. No, you do not get to work with it. I might. Dang. Right? Diazomethane acts as a nucleophile and an electrophile simultaneously. It has this negative and positive characteristic associated with it. The carbon will act as that electrophile and nucleophile. And for whatever reason, I couldn't draw that Lewis structure, which is really embarrassing. Okay? MCPBA, the peroxy part. There's our reactivity. Why is it reactive? Because those electrons want to go that way. Why would they go that way? Resonance, stabilizing those electrons. Okay? So that purple oxygen becomes super, super positive. Okay? It also still has a pair of electrons, meaning it can still act as a nucleophile. Okay? The mercury acetates. Why do those electrons want to move that way? Resonance. We would kick out a good, stable leaving group. Okay? So the mercury would act as a positive to lose that leaving group. But mercury, being a metal, also has electrons. So it can also donate those back in. Make sense? All right. So let's take a look at some practice with the cyclotri intermediates. For those of you that know your reagents and want to keep jumping out to the final product, don't, because I didn't ask for that yet. Okay? So attempt these real quickly, see what you can come up with. And yes, real quickly, I'll give you 3 minutes. Br2, we're forming that Br positive, which gets us that cyclic intermediate, which means when we go through and draw our final product, we have to say, is that cyclic intermediate something that is stable? Some people have already answered that. No, it is not stable because it's positively charged, which means I'm going to put a bromine at both positions. That's where I would start first. The next part, do I have any stereocenters? Yes, which then means I need to show the wedges and dashes. So if I make this one wedged, what does the other one have to be? Why does it have to be dashed? Okay. This is a backside because that cyclic intermediate, the only way it breaks is we do a backside attack with our nucleophile. So it's recognizing our intermediate stages along the way. I'm going to go down first and then we'll go to the second column. Actually, I'm going to go counterclockwise through these. The next one with the mercury reagent. The mercury reagent forms that kind of intermediate again. Okay. What's my nucleophile though to break that open? Water ends up being the nucleophile. Water will come in and attack. Where does it attack? The backside. Is there a difference now on the backside?
Yes.
Yes. One backside is better than the other. Is the leaving group a good leaving group?
Yes.
Yes. We don't want a positively charged species there. That leaving group is already trying to leave, which means the water is going to attack. Yes, the back has been established. Most or least sterically hindered? The most sterically hindered. The result, officially we would have the oxygen with a positive charge. We'd have our mercury attached at the other position. Okay. What's going to happen with that positively charged oxygen? It'll lose the hydrogen. We'll end up with that as our product. Okay. Do I like having mercury attached to my organic structures? No. That would require a second reagent to finish that. We'll deal with that later. The next one, our peroxy structure. The oxygen acts as both the nucleophile and the electrophile. So if we cleaned all that up, we end up forming our 3-membered structure. Stable or unstable? Okay, I heard a little bit of both. Why are you saying it's stable? No charge in the oxygen. Why are you saying it's unstable? Nope. Okay, so it's stable. Good call. Do we have a stereocenter? Yes, which means I need the wedges and dashes. Okay. Or just wedges. If I provided this as my answer, technically also all the way up to the top one too. Same question. Are those correct? No? Why are you shaking your head no, Amber? If it helps, you're right. Remember, these are pi bonds. The pi bond can attack both above and below. We also have the enantiomer. Bottom one we can say plus enantiomer. The top one we can't get away with saying plus enantiomer because what is special about that carbon? Well, actually, well, that's not a stereocenter. We can get away with that one. I lied. Plus enantiomer. Okay. Last one, the upper right-hand corner. That one looked all sorts of weird. Okay, and I would bet you had a little bit of trouble figuring that one out unless you happen to remember seeing it in the past. Okay, when we look at those reagents, we do not inherently see, or at least I don't think we see, the carbene that we just talked about. Okay, Okay? Diazomethane was one way to get a carbene. We could also do it this way. Okay? When you look at your reagents, you can be thinking, okay, it's this reaction because I memorized these reagents, that means it's this answer. Or you can look at the reactivity. We have an alkene, we have chloroform, and we have sodium hydroxide. If we pull the face test on those, which of those you're going to be like, do not throw that in my face? Probably a couple on your list in there. Chloroform just knocks you out. What is sodium hydroxide going to do? All sorts of wicked witch of the west or east kind of stuff. That's not pleasant. Let's avoid the sodium hydroxide. Why is it reactive? What makes it reactive? Whoops. The negative charge on the sodium, which means really we're looking at a negative hydroxide. Would I expect the negative to react with the alkene? Nope. What does that mean the negative needs to react with? Something positive up here. What is that something positive? The hydrogen in an acid-base reaction. Why is that hydrogen acidic? What's that? Did you guys say? Why is it partially positive? That's a hydrogen connected to a carbon. Is that a particularly acidic hydrogen? No. Why is it acidic now?
Because of the chlorines.
What's the reasoning? Chlorine, yes. What is our reasoning for why that hydrogen is acidic? It's the inductive effect. 3 electronegative chlorines withdrawing electron density, that makes that hydrogen acidic. Okay? So the base can come in, remove that hydrogen. We now have that negative. Chlorine's a good leaving group. It can pop off. We have our carbene. The carbene can now react. The result, this is the one I think I actually wanted. Do we have any stereocenters? Yes. Do we need to label them? Whoops. Yes. Let's say this was wedged. What does that mean? The only one that's red. That one is red. That one is wedged. What does that mean? The other one has to be wedged. What else does that mean? That one has to be dashed. Okay? Can I say plus an enantiomer? No, because that methyl group did no chemistry, which means it did not change, which means I do not have enantiomers. Okay? This is where it gets dicey on a show your work. Technically, you would have to show both. Right? Showing one shows me that you understand the chemistry. I would accept that for most credit. To get full credit, you would need both. It takes time to draw both. Draw one. If you get time, come back, draw the second. Okay? Make sense? With that, sorry, we have to be done.